If you want to design your own implementation of the linked list, you can choose to use a singly linked list or a doubly linked list. So a node in a singly linked list should have two attributes, val and next. Val is the value of the current node, and next is a pointer reference to the next node. But if you want to use the doubly linked list, you will need one more attribute, preview, to indicate the previous node in the linked list. So let's assume all nodes in the linked list are 0 indexed. So let's start from the simplest possible myLinked list, which contains just a structure size and a sentinel head. So we should note that the sentinel node is used as a pseudo head and is always present. So this way of structure could never be empty. It could contain at least a sentinel head. So all nodes in my linked list have a type list node value plus link to the next element. So let's set a class my linked list, and we define double underscore initialized self. It have two parameters, self dot size, which is default value is 0, and self dot head, which is our pseudo head 0. So this is sentinel node using our pseudo head, and then we can define another class list node, define double underscore initialize double underscore self. It has a x parameter, self dot value is x, which is the node is self's value, and self dot next is default value is none, which is connect to node. Let's say we have a linked list which is 0 pointing at 2, pointing at 3, pointing at none, and we all know 0 is our sentinel head. And if we want to insert the 2 add, which is list node, the argument is val. If we want to insert it at the index 1, we should first find our predecessor, which is index 0 at this case. If we want to insert, the first action we need to do is link the 2 add with the next node of the predecessor. Then we just unlink the predecessor 2 with 3, but link the predecessor with our new node 2 add. So this is our insertion at specific index. So finally we get 0 pointing at 2, pointing at 5, pointing at 3. And then we should increment our length of the list because we just add one element. So let's try to define add at index. We have to input self, and index is where should we insert, which is integer, and val is what we want to insert. It is also an integer, and then we output none, which means it will didn't output anything, but it will change the node itself. So first we should consider the edge case. If the index is greater than the length self dot size, so in this case this node will not be inserted, we just return nothing. And then another edge case, if the index is negative, if the index is less than 0, then the node will be inserted at the head of the list, which means we assign the index by 0. And then after we insert, we should update our size, which is incremented by 1 because we just add one element. And before we insert, we should set a predecessor, which is initialized to self.head, which is the beginning of the list. And how do we find where should we change the predecessor? We will set a for loop for underscore in range from 0 to index. And the predecessor is every time updated by predecessor.next until it meets the index. So then we set our node to be add. It is 2 underscore add, and it is list node. The argument is val, and we can insert now. The insert itself have two actions. First, we link the 2 add with the predecessor's next node, and then we link the predecessor with to add. So we are done. This is our insertion. If we want to insert node at the head, we will call the function self.add at index 0 val. So its predecessor is a sentinel head. We just add a node of value val before the first element of our linked list. So after this insertion, the new node will be the first node of the linked list. So this is our add at head operation. So if we want to insert node at tail, we have to call the function self.add at index self.side val. So its predecessor is our last node. If the index is equal to the length of linked list, the node will be appended to the end of our linked list. So we just append a node of value val to the last element of our linked list. So this is add at tail operations. So let's try to define add head. It only have self and val, which is the integer as input, and output null mean nothing, because we just insert at head, so we don't have to know the index. We just call the function self.add at index, which is 0, the first element, and val, and then we define add at tail, which have self and val, which is integer, and output null. And we also call the function self.add at index, and it is last element, so it is self.size and val. So first, according to the index we want to delete it, we can find our predecessor, and then we just connect our predecessor with the next node of our predecessor, and then we should update our size of the length, which is self.size decrement by 1, because we just remove one element. So let's try to define delete at index, which have self, and index is integer, is where we should insert, but we should notice we don't have value, because we don't have to know the value, we can just delete it, and it will return none because it will just change the node itself. So if we want to delete the index node in the linked list, first we should consider if the index is valid. If it's less than 0, then it's negative, it's not valid, or the index is greater than the size of the list. This means also beyond the boundary is not valid, then we just return and finish the algorithm. So every time we delete, we should decrement the size of the list, decrement by 1, and then before we want to insert, we should consider to find the predecessor of the node. Where should we delete, right? The predecessor is first reset to the self.head, which means the beginning of the list, and then we should update them by for underscore in range from 0 to index. So every iteration we will update our predecessor to move to the next node, and then after for loop we will find our predecessor, so we just delete the next node of predecessor, which is link the predecessor with the next node of predecessor, which will skip the next node of predecessor. This is how it's deleted. So let's try to define get, which have self and what index we want to search, which is integer, and what value we finally get, which is also an integer as return. Then we should first check whether the index is valid. It's less than 0 means negative, is not valid, and if it is greater than or equal to the length, the size, then it is also invalid. Then we return -1. So let's start. First we set our current is to the head self.head. Then we can start iterate by for loop for underscore in range from 0 to index, and we have to +1 because it is include index itself, and every time we just move to the next node of the current dot next. Then finally we can just return current dot val to get our value. So let's analyze the space complexity, which is for all the operations. The space complexity is of 1 because we didn't use any extra space. But for time complexity, every operation is totally different. For example, the gate operation, the time complexity is O of k, where k is where we have to find our element to iterate k times. And add at the head is O of 1 time complexity because we just directly add at the head. And for add at tail, the time complexity is O of n, where n is the size of the list because we should iterate the size of the list, right? And about add at the index, the time complexity is O of k. We just stop until we find it. And same delete at index is also O of k because we only iterate O of k time.